So in one-class learning, you are given samples from the positive class only. In your training set, and the task is to detect outliers. And I think I can best illustrate this by example. So the methods that we will look at, so here's a small 2D example for different parameter settings, will or will not identify these points up in the corner as outliers. And well, that is useful in applications like the following. People here on campus acquire zillions of images using robots, so images of cell cultures, and sometimes things go awry. But you know, if already during the setup of your experiment you would find fingerprints or defocus and such problems, well, you would probably try and fix these problems in the first place. But supposing that you couldn't do that for some reason, then you could train a supervised classifier. So you could train something that will tell you, is a big white blob, is that a fingerprint or not? Because you see, if you want to measure things like the average expression level of some gene, then if you don't recognize this sort of problem, and if you don't recognize it automatically, this will of course mess up your analysis. Because you know, if you're interested in how much white is there in this image, then you don't want to count this blob. And in one-class learning, you're only given examples of good images, so images that are certified to be without problems, and then you want to find all kinds of deviations from these good images. And here's something that Christian Schelen, a master student, did. So he would compute all kinds of features locally first and aggregate these onto patches, and would then have examples of good patches as to train this one class SVM, and could then in the future detect other problems that other images might have. So here's an example of some of the features that can be computed. It's all very colorful, but all of this results from the single image that you see here on the left-hand side. And then perhaps you see these faint red lines that outline problems in images that he processed automatically. So this is something that you want to find outliers, and you could use the kernel density estimation for that that we've briefly discussed today, or you can use support vector data description or the one class SVM. Now, in support vector data description, what you do is you find in the high dimensional space a hyperball that comprises only the good observations. So you want to find the minimal circumscribing hyperball in your high dimensional space. And we will, so let's say you have observations and a few outliers, then your hyperball may look something like this, and you would then have a couple of outliers which we associate with slack variables. So if this is observation number 12, this would be slack variable number 12, and so on. So these are support vectors here, and then we typically have some support vectors that lie exactly on the boundary of the hyperbole. And again, the hope is that you have a much larger number of points which are not being support vectors, thus giving you a sparse representation. So I will do the math. This is very, well, it's similar to what we did last week, but I think it will help repeat those concepts. So we're trying to find the smallest possible hyperbole. For mathematical convenience, we will again use the square of the radius. And xi are the slack variables, such that the following conditions are fulfilled. I am this time writing explicitly the mapping to a high-dimensional space. And B is the center of the ball. And we want the squared Euclidean distance of each of my points from the center of the ball to be smaller than this radius r, except that we admit some slack here. Slack variables should be non-negative. And we minimize over r and b and xi. And again, xi are the slack variables. B is the center of the ball. And r is its radius. And like last time, we built a Lagrangian, which has both these primal variables and the dual variables, the Lagrange multipliers that we use to enforce these two sets of inequality constraints. Last time I weighted the sum of these slack variables with a constant c. This time I'm writing 1 over nu times n. N is the number of points, and the idea is that normalizing by the number of points here will give you something that's more independent of the training set size. And nu is now your user chosen parameter, so it's you know, last time we had to fix c as a design parameter, and this time you have to fix nu. Same thing. It's the user design parameter which trades off how much slack you want to admit. So a non-robust version of this, let me draw a non-robust version for the very same data set, or try at least. I guess it would look like that. So imagine that this is a circle, this purple thing. Then that would be the hard margin solution where I admit no slack. And if I do admit some slack, then the hyperbole will, well, it will become smaller, and it will be able to flag these outlying points as outliers, which is my aim. So this trade-off has to do with the sensitivity that you want to have versus the number of false alarms that you will get in your method. Okay, now I add to the Lagrangian these inequality constraints. So I'm using, again, alphas for the first set of inequality constraints. So I'm saying that I had the Euclidean distance, so I'm writing this here as a product of vectors. So here's my Lagrangian, and I now differentiate it with respect to the primal variables first. So R appears here. And the Karush-Kuhn-Tucker conditions tell me that I want to have an extremum with respect to these primal variables. I'm setting these derivatives to 0. And thus get the following condition out. See, I can divide by the 2R, and then I'm left with a 1. So I'm finding that sum over I alpha I is 1. That's the first condition. And then differentiating with respect to the ball of the center. So B appears here. So I have a B squared, which I differentiate. And then I have a mixed term of 2 times the phi and the B, which leaves me, note the negative sign here. Okay, and again I want this to be 0. And the equation before told me that the sum over I alpha is 1. So I find that B is this. Finally, I differentiate with respect to the slack variables. It also appears here. Gives me minus alpha I. And then there, minus mu I. Okay, then I can build the Wolfe dual. So I insert the optimum values for the primal variables. And will then optimize with respect to the dual ones. Now here I get an inner product of the phi transpose phi, which I can write directly as a kernel. Okay, like last time, we will find quite a few things to simplify here. So the sum I alpha I was 1, and then I can cancel here this r squared term. Then the nu I can use this condition here to say this is 1 over nu n, and then this cancels with that. Then this equation here tells me that this is in fact B. So I'm left with not much, namely minus B transpose B. Or to express it fully in terms of the dual variables, this is so I'm using this equation here to express B again in terms of the Lagrange multipliers. And like last time, the condition that mu I should be non-negative, and we know that alpha I plus mu I is that. Together it gives me this upper bound on my Lagrange multipliers. And we still have this. The sum of the Lagrange multipliers here must be 1. Okay, now this is the Wolfe dual that now needs to be maximized with respect to these dual variables, with respect to the Lagrange multipliers alpha. Once we have found the alpha, we can, by this equation find B, and we still need to find R also. And to find R, remember that the support vectors that really lie outside the margin, so if I take this as the solution here, then the support vectors outside the margin will have the maximum values for the Lagrange multipliers. So I know that here, for instance, this support vector has taken its maximum value, but the support vectors which lie on the boundary, they have some intermediate value. So larger than 0, but smaller than this upper limit, if this here is sample J. And this condition can be used to find the optimum value of the radius. So the radius is defined by sorry, it's an equality now, where xi is any support vector which has a Lagrange multiplier that takes a value larger than 0 and smaller than this upper limit. This should be a strict smaller here. Okay, and if I want to solve here, or if I want to insert what I found for B, I can rewrite this as the kernel. So I'm simply inserting into B this relation here, and I'm writing the inner product between two vectors phi as a kernel. And that gives me the following. Sorry, it was too fast? Okay. So, yes, go ahead. The mu was the slack variable that the mu was the Lagrange multiplier that enforced the non-negativity of the slack variables. Okay, so I could write this as psi I minus 0, and I'm omitting the minus 0. So you see the pattern is I'm taking a Lagrange multiplier alpha I, and then this minus the left-hand side. And here I could have written this as in the same fashion, but the one side of this inequality was not very interesting, so I omitted it. So this was very similar to the derivation for the SVM. We get out an optimization problem, which I've written in not so pretty handwriting here in this box. And we can make this even more similar to the normal SVM if we consider translation invariant kernels. Or we can bring out the similarity even more by considering translation invariant kernels. And this is what the one class SVM does. So whatever position x we put in there, the kxx is constant. And if you glance at our optimization problem again, here we had the kernel evaluated at xi and xi. So in other words, this thing becomes a constant here and can be omitted, because what's left is the sum over the I alpha I, and the sum I alpha I we had seen is 1, so that for translation invariant kernels, this first term here makes no difference to the optimization problem. Okay. This defines the one class SVM. And this formula is now very, very similar to the soft margin SVM. Just for comparison, the soft margin SVM for classification looked like this. We had a minimization over the following. And somewhere we had the condition that this holds. Now, you see the labels have disappeared because in one class SVM we only have members of the one class. On the other hand, for the classification SVM, we had this extra term, which we don't have because we know this is constrained to 1. And that also matches up with this equation here. So this equation tells you that for the normal classification SVM, the Lagrange multiplier is weighted with the class labels from the two classes must sum to 0, so they can be +1 for one class and -1 for the other class. Here we just have them for the one class. Okay. Now, what does, in terms of interpretation, what does it mean to have a translation invariant kernel? K of x being constant means the following. So if we have k of x, which is the inner product of phi with itself, if we have this constant, this means that all observations in this high-dimensional space lie on a sphere with this radius here. So I'm here showing the first coordinate of this high-dimensional mapping, and I'm here showing the second coordinate of this high-dimensional mapping. And I here have a sphere. And I know that if I use a translation invariant kernel, all my observations lie somewhere on that sphere. And observations that are, well, similar, that have a high similarity, you know, they obviously lie close together on this spherical surface. And then we can have very dissimilar observations that are at almost right angles to each other. And this sphere has as many dimensions as your mapping or as the feature space that you use. Now, what we did with the support vector data description was that we found a circumscribing hypersphere. Let's say, I'm thinking about which color here is best. Let's take this one. So let's say this would be the solution of the support vector data description. And here I used slack variables that looked like this and like that for the outliers. Now with the one class SVM, what we effectively do is that we separate all points from the origin. So in the one class SVM, the origin represents all outliers. And the reason is that if we take any vector phi and multiply it with the 0 vector, well, we get out 0. So the kernel between any observation and 0 must be 0. So another way of saying this would be to say that the origin represents all points that have a low similarity to the training set. Now in this one class SVM, there is no talking about balls or anything. Here we just have a hypersphere and, a hyperplane, and we want to maximize its margin. So This would be the margin, and if you wish, I can also draw the actual decision boundary. And this is now the one class SVM, which also has slack variables, but now the slack is measured as distance from this hyperplane. And well, because the optimization problem for the one class SVM was derived from the optimization problem for the SVDD, under the only restriction that we're using a shift invariant kernel, it means that the solutions must be the same. They must have the same support vectors, and indeed both this hyperball and this hyperplane, they cut out the same parts from the original sphere. So you see that the hyperball, the blue object here, it took these points as inliers and the rest as outliers, and the hyperplane also kept these points as inliers and the rest as outliers. And again, remember that all outliers must also lie on a sphere because we're using a translation invariant kernel here. So for a translation invariant kernel, support vector data description gives you the same as a one class SVM. And the hyperball that we use for the support vector data description and the hyperplane that we used for the one class SVM, they both cut off the same spherical cap from the sphere that holds all observations. So in my sketch, the hyperball here was blue and the hyperplane was red, and this sphere holding all observations I had drawn in black. Okay, this was the sphere holding all observations. Now I found this quite puzzling when I, for the first time, only by reading, realized that for such shift invariant kernels, all observations lie on this sphere. But I hope you are convinced by this argument here. Yeah, so they all have the same radius. They lie at the same distance from the origin.